So last week we looked at how to solve polynomial functions given 1, 0. But now we want to be able to solve any polynomial equation even if we're not given any zeros, we're not given any solutions. So we're going to be looking at the rational root test or rational root theorem. Its job is to provide us with a list of possible zeros. And then we're going to test those to see which ones actually work. So remember, what we're trying to do is we're trying to find all the factors. So remember how you find a factor, right? So find all the factors of 6. So obviously the factors of 6 are 2 and 3 because 2 times 3 is 6. Factors from numbers, relatively easy for us. We've been doing that a long time. Factors in polynomials, not quite so easy. So here's how we're going to do it. To find the possible rational zeros, we're going to look at the constant term, that's this guy right here, and we're going to look at the leading coefficient, that's this guy over here. So then to take a look at what might be possible zeros or possible roots, we're going to put the factors of this guy in the numerator and the factors of the leading coefficient in the denominator. Let's take a look at a problem. First problem, use the rational zero test to list all possible rational zeros of each function, then verify the zero shown on the graph is contained within the list. Okay, so let's look at factors of the constant. So factors of 3 are plus and minus 1 and plus and minus 3. Factors of the leading coefficient, remember the leading coefficient over here is a 1, is plus and minus 1. So 1 divided by 1 is 1, then obviously plus or minus, and then 3 over 1 plus and minus 3. So how do you verify that one of these is going to work? Well, you have to use synthetic division, right? So let's try negative 3 and just verify that negative 3 works. So if I put in negative 3, negative 3, this would be 1, 3, negative 1, negative 3. Aha, it works. So, and this is x squared minus 1, right? So what I'm left with is x plus 3 times x squared minus 1, and this factors into x plus 3, x minus 1, x plus 1, and my zeros are negative 3, 1, and negative 1. Oops. And negative 1. So from this list, you can see that positive 3 was in this list and not an actual 0. Remember that this list only represents things that might be zeros, and then that's the list we use to start testing them using synthetic division. So let's take a look at example 2. So again, we're going to look at the constant. Here's the factors of 2. And we're going to look at the leading coefficient. Here are the factors of 4. And make our list. So our list is going to be plus and minus 1, plus and minus 2, plus and minus 1/2, plus and minus 4. Oops, 1/4. We don't have to check 2 over 2 because that, again, is just equal to 1. We already have that number in our list, and we don't have to check 2 over 4 because we already have that in our list. That's the root 1/2. So now we want to start checking some of these, right? So let's take a few minutes to check some of these. All right, let's test one. It's an easy one to test. Okay, my coefficients are 4, -8, -5, 10, 1, and -2. Okay, -9, -9, 1, 1, 0. Oh, that's 2, 2, and 0. Okay, so it does in fact go in evenly. We got a remainder of 0. So one of the things that we know works is we know +1 works. If I want to continue to break this guy down, I would continue to use synthetic division. And I would continue to check possible roots from my list until I could break it all the way down. So we just seen that we're going to test some of these, right, using the trial and error process of synthetic division. Okay, so we're hoping that one of them is going to give us 0 as a remainder, and then that means that that's a factor, and then of course we'll look to see what is the 0 of that factor to find the root. So this one says find all the zeros of the function. So again, let's look at the factors of plus or minus 6, 1, 2, 3, and 6. Let's look at the factors of the leading coefficient, which is just 1. And then my list of possible factors are just going to be these guys, right? All right, so let's test some of these. All right, let's give -1 a try. 1, 2, -5, -6. Oops, that's -1, -6, 6, and 0. Okay, so we have x plus 1, that's the factor associated with this 0, times x squared plus x minus 6. That's the polynomial associated with this depressed polynomial. Let's continue to factor. X plus 3, x minus 2. Therefore, my zeros are going to be -1, -3, and +2. All right, let's look at the next one. So, write the polynomials as a product of linear factors. Well, we just kind of looked at that, right? We said that if 1 is a 0, -1, that x minus a -1 or x plus 1 will be a factor, right? So we had x cubed plus 2x squared minus 5x minus 6. We know that x plus 1 was a factor, and when we divided it out, we found out that x squared plus x minus 6 was also a factor. And as we kept going, we knew that we could break this down even further and write this as x plus 3 times x minus 2. So there we go. We've taken this third degree polynomial and written it as the product of 3 linear factors. And we should be able to match the number of linear factors to the degree of the polynomial. All right, find the zeros of each function and write it as a product of linear factors. So again, right? First, let's look at the factors of 8. That's the numerator. Then we're going to look at the factors of the leading coefficient, which is just a 1. That means that this is my list of factors. I'm going to use synthetic division to test. Let's see. Now you might be wondering, how do I know exactly which factors are going to work and which ones aren't going to work? I actually don't, but for the sake of time today, I'm intentionally showing you the ones that work. Okay, so 0, 0, 4, -8, 0. Okay, so now we have this turns into x plus 2. This turns into x squared plus 4. Now, obviously, if we're going to solve this, we're going to take this guy and set him equal to 0, and we get x equals -2. But when we take this guy and set him equal to 0, we're going to get x squared plus 4 equals 0. X squared equals -4, and x equals plus or minus 2i. So my roots are going to be -2 and then plus or minus 2i. So, did you notice that in the last example, the complex numbers were conjugates? This illustrates a very important point, and that is that complex conjugate roots always come in pairs. I call these guys twins, okay? They're like fraternal twins. They're almost the same. Not quite. A plus bi and a minus bi. If you have one root, a plus bi, you will always have its conjugate root, a minus bi. All right, one more time. Let's look at the factors here. Plus and minus 1, plus and minus 5, plus and minus 25. And the factors here, plus and minus 1, and plus and minus 2. So my choice for factors are going to be 1, 1/2, 5, 5/2, 25, and plus or minus 25/2. Okay, it's going to seem like an amazing guesser, but I reworked these, pre-worked these, so let's use 5/2 as my root. 2, -15, 23, 15, and -25. So that's 5. That's -25. That's -5. And that's positive 25. I need to break this polynomial down right here, this guy. I need to break him down, and I don't know how. So what I'm going to do is I'm going to continue to use synthetic division, and I'm going to use, I already ruled out 5/2, and I'm going to use another potential root from over here to test again. So I'm going to break down this polynomial by using the root of -1, and now I'm left with this guy. Okay, so what do I get? I get this guy right here, x minus 5/2. I've got this guy right here, x plus 1. I've got this guy right here, which I'm going to pull a 2 out of, x squared minus 6x plus 5. Keep factoring one more time. X minus 5/2, x plus 1, x minus 5, x minus 1, and that means my roots are going to be 5/2, -1, positive 5, and positive 1. Just because we're learning how to use the rational root theorem doesn't mean you should use it on a problem like this. Use quadratic type. Just because you learn the rational root theorem doesn't mean you should use it on a problem like this. Just take out the greatest common factor and then factor the remaining quadratic.